Bismillahirrahmanirrahim. Today, inshallah, I'd like to talk about binomial expansion. First of all, let's appreciate the term, what this really actually means. A binomial, if you recall, is a two-term algebraic expression like this. So a two-term algebraic expression such as a plus b is a binomial. An example would be 3x plus 2. Another example would be x squared plus 4y. These are both binomials. So all of these are examples of binomials, two-term algebraic expression. Now, what we mean by binomial expansion is this. That is, if we are given a binomial, such as this, a plus b, to a certain power like this. Now, when we multiply this out, such as a plus b times a plus b, and we have done this before, obviously. Now, this will be, of course, as you recall, a squared plus 2ab plus b squared. Okay? And this form here is the expanded form. So this is the expanded form of this algebraic expression. So this is the binomial, and this is the expanded form of the binomial. So that's what we're going to do today. So for example, if we have a plus b to the third, this is the factored form, and if we wanted to write this in the expanded form, we would multiply this out as follows: a plus b times the quantity a plus b times the quantity a plus b 3 times, like this, because it's a plus b to the power of 3. And which would basically be this multiplied another time like this, a plus b, like this. So that's what we're going to do today. We're going to take binomials and we're going to expand them, let's say, to a plus b to like 7th power. And what would this be in this expanded form like this? Well, you might say, why take a perfectly normal, happy day and ruin it like this by doing binomial expansions? Well, because it's valuable. It's important, you will say in the future. Somebody else might say, on the other hand, why take a perfectly beautiful day and embellish like this by doing binomial expansions? It's true, beauty is in the eye of the beholder, isn't it? So anyway, so we're going to learn how to do these binomial expansions. Now, if you recall from before, we have done this before, and this is basic knowledge which you need to kind of have like memorized. We have done these basic binomials. A plus b squared is a squared plus 2ab plus b squared. And just this is a review. A minus b squared is a squared minus 2ab plus b squared. And then we had the product of the difference, a plus b times a minus b, and that was a squared minus b squared. And that's very basic, and you should really know that, because you really can't escape that. All right, so that we have done before. Now what we're going to do today is I like to show you something, and we're going to expand this. So we have a plus b is the most basic of binomial, first of all, to the 0 power. Okay, and then we're going to have like a plus b to the 1st power, and then we're going to have a plus b to the 2nd power. We're going to expand all of these, and we're going to have a plus b to the 3rd power, and then we're going to have a plus b to the 4th power, and then we're going to have a plus b to the 5th power. And if you're getting scared, don't worry, I'm going to be doing the math anyways. So here's a plus b. So of course, a plus b to the 0, anything to the 0 power is 1. And a plus b to the 1st power is just a plus b. So I'm just going to write that as 1a plus 1b. And we've already done this before. You can FOIL this. Say if you have a plus b times a plus b, and you can FOIL that. And if you really have to understand, FOIL means, now each letter in this acronym represents a product. So the first means the product of the first terms. the O means the product of the outer terms. The I means the product of the inner terms, and the L means the product of the last terms. So if you do that, first, outer, inner, last, the product of the first, the product of the outer, the product of the inner, and product of the last terms, you get A squared plus AB, and then inner is BA or AB, and product of the last term, and that's B squared. And you simplify this as A squared plus 2AB plus B squared, like this, correct? So we've done that before. So I'm just going to write that over here because we're so familiar with this already. So this is, I'm going to write that as 1A squared plus 2 times A times B plus B squared. Now to get A plus B to the cubed, you can just take this, right, and multiply it one more time by A plus B, like this, and then you write that over here, correct? Well, that's what we're going to do over here, all right? Now, you saw how I did this. I multiplied these out one at a time, and I combined the like terms, and I got this. So A plus B cubed is 1A cubed plus 3A squared B plus 3AB squared plus 1B cubed. Now, to get the fourth term, I have to take this and multiply it again by A plus B. And without doing the whole work, because I don't want to torture myself, I'm just going to tell you what it's going to be. So it's going to be 1A to the fourth plus 4A cubed B plus 6A squared B squared plus 4AB cubed plus 1B to the fourth. So that's pretty good. All right, so and then the last one I'm going to tell you, it's going to be the following. It's going to be 1A to the fifth plus 5A to the fourth B plus 10A to the third B squared plus 10A to the fourth B cubed plus 5A, I'm sorry, I meant to say over here, I wrote this wrong, you didn't check me. So A cubed B squared, A squared, B cubed, I'm sorry, plus 5A B to the fourth plus 1B to the fifth. It's actually not easy talking and writing at the same time. Anyway, so here it is. So I've done this binomial expansion. Now, clearly, it's not something that anybody particularly enjoys to do, except for a few perhaps. So, and obviously there's a good reason for this, why we're doing this, a useful reason for this, and otherwise we wouldn't be doing this. But somehow I got these without doing this. It must be a trick, right? So you'll see some patterns in this, okay? So the first thing that you must observe is whatever the power is over here, all right, whatever the expansion degree is, but that's the first, that's the degree of the polynomial. So if it's A plus B to the fourth, that would be the degree of this polynomial, with A to being to the fourth. So A plus B, the quantity to the fifth, would be, this is the fifth degree polynomial with respect to A, correct? So that's the first thing that you have to understand. So the first term will be A to the whatever the maximum power. So if I have A plus B to the 15th, the first term will start out as being A to the exponent of 15th. Okay? And then what you will observe, of course, so that's the first thing that you have to observe. So let's take this one as an example. So it's A to the fourth, and then you'll observe that the exponents of A will continue to go down by a power of 1. And there's A here, and then it's A to the 0, as you can see. So they continue to go down by 1. So it's a to the fourth, a to the third, a to the second, a to the first, and a to the 0 over here. All right, that's the first thing that you'll observe. And so the exponent over here, the expansion exponent, if you like to say, will determine the a. Okay. The second thing I hope you appreciate is the following, is that the b does the opposite thing. So here b here is 0, and b to the first, b to the second, b to the third, and b to the fourth. So a goes down like this, and b goes up like that. All right? And in the middle, they're the same, like over here, for example. They happen to be the same in this case because it's an even power. So that's the second thing. The other way of looking at that, probably a more useful way you will see in the near future, is that if a to the fourth and a to the third, a to the second, a to the first, you'll see that a and b, the exponents, will add up to give you the power over here. So a to the fourth means b has to be 0. A to the third means b has to be 1 because they add up to give the 4. So the powers add up to give the exponent. So this is a to the fourth like this. So this is a very useful trick because then you can generate any of these in terms of at least the a and b. So if I have a plus b to the 17th, all right, I will start off as, okay, well, a is going to be the 17th, okay, and then b is going to be 0, okay, and the next term is going to be a to the 16th, and they have to add up to give you 17. So so the b is going to have to be 1, and the next term is going to be a to the 15th, and b is going to have to be 2 because they have to add up to 7. And the last term is going to be a to the 0, or just 1, and b to the 17th, like this. Okay. So you can see that's not too bad. Okay, we got that. Okay, so the exponents of a are declining like this, and the exponents of b are declining like this, and they add up to give you the power over here. The only other thing over here is that the coefficients over here. All right. Now the coefficients there are kind of funky, right? So, well, that's the only thing that we would have to figure out if we're going to do this. How are we going to figure out those coefficients? Well, what I'm going to do next is, and you might or might not anticipate this, so what I'm going to do now, I'm just here going to write down the coefficients. Here, a plus b to the 0 is just 1, so I'm just going to write that 1 over here. And then I'm going to write these coefficients over here. It's 1 and 1, correct? So it's 1 and 1. And then I'm going to write these coefficients over here. That's 1 and 2 and 1. And then I have 1, 3, 3 and 1. And as you can see, and the next one is going to be 1, 4, 6, 4, 1. And of course, you recognize this as the Pascal's triangle. In other words, the coefficients of the binomial expansion can be derived from the Pascal's triangle, and here they are. So the coefficients of the binomial expansion can be seen in the Pascal's triangle. Okay, so, and that's pretty easy enough. All right, now just to give you as a review, because I know we have covered this before, when you write out the Pascal's triangle like this: 1, 2, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5. Some of these is 10, 10, 5, 1. That's of course how I got this particular row. When you write out the Pascal's triangle like this, okay, this row, these are all rows. This row is not the first row. It's given the row to be like 0. Okay, that we'll call that R. That row number 0. Okay. Well, let's just call it row. For now, we'll call this row number 0. And the nth row, if you had the nth row, let's call it n is equal to 0. This row is going to be n is equal to 1. That's the first row. This row is going to be this particular row is going to be n is equal to 2. So the row numbers for the Pascal's triangle don't start out as 1. They start out as 0. And that's kind of like super duper important for you to remember. Did I say super duper important for you to remember? Yes, it's super duper important for you to remember. Okay. All right. And then if you wanted the coefficients of any particular binomial, okay, then you go to that row. So this is the what? This is the fifth row actually, because this is 0, 1, 2, 3, 4, 5. So whichever, so a plus b to the 17th, okay, that would be the 17th row of the Pascal's triangle, okay, starting with n equals 0 like this. Okay, so that's very important to understand. So the coefficients of the Pascal's triangle give us the coefficients can be derived from the Pascal's triangle. All right, so the next step is the binomial theorem. See, when you're expanding a binomial like this, so let's say you have a plus b to the fifth, there are two things that you have to do. First, you have to just kind of like write down the a's and b's over here. So you have a, and I said start with the power over here, a to the fifth, and then the b will be 0, right? And then I go down by 1. I go down by a to the fourth, and b will be 1 because they have to add up to 5. And then the third term over here, a will be 1 less, and b will be 1 more, and they would have to add up to 5. So that's a, b to the fifth. And then you have a squared, b to the third, and then I have a to the first, b to the fourth, and the last term would be a to the 0, or just 1, and b to the fifth. That's the first thing that I have to do. And then the second thing, though, is I have to write the coefficients of these, like this. Okay? So there are several ways of getting them coefficients, actually, and then the most coolest way we will learn in the near future, inshallah. But the second coolest way, I'm going to say, is probably this polynomial, is the Pascal's triangle. So you go to the fifth row, understanding that's basically the one that starts with 5 over here like this, and then understanding that this is row number 0. Okay, that's the 0th row. So you go to this row over here. So that row is n is equal to the 5. That's the fifth row of the Pascal's triangle. And then you just kind of like, you know, steal the coefficients from there. So I write 1, 5, 10, 10, 5, 1, and I'm done. So, and then to get to the sixth row, if I wanted to do the sixth one, I would just, that's what I would do. I would do 1, 6, 15, and then 20, 26, 1, and these would be the coefficients of this binomial expansion like this. Those would be the coefficients over here, and I can also write a's and b's in the way that I have done in the previous example. Okay, that's easy enough, you would say, right? Okay, so that's what we have to do. If we want to do a binomial expansion, we can just get the coefficients from the Pascal's triangle and do this. Okay, well that's kind of hard, because if I told you this, a plus b to the 17th, first of all, you have to draw out the Pascal's triangle all the way to the 17th row, and you have to better make sure you don't make any computational mistakes, right? You know what I'm saying? So it's kind of difficult to do that. But it so happens that these coefficients also have a pattern of their own. And the pattern that is these coefficients over here, they have a pattern, and that relates to combinations. In other words, these coefficients, if I just write down the fifth coefficient over here, 1, 5, 10, 10, 5, 1, these can also be written as combinations. Okay, so if I were to just write down the fifth row over here, that's like over here. Let's say I wanted to do this. Okay, and I did not want to draw out the whole Pascal's triangle. So, and I wanted to derive this this term over here, the fifth row of the Pascal's triangle. Remember, the fifth row of the Pascal's triangle, n is equal to 5, it starts over here. And so it turns out that very conveniently that this row is basically a series of combinations such as this. So the first term is in fact combination of 5, choose 0, and this is combination of 5, choose 1, and then 5, choose 2, and this is 5, choose 3, and this is combination of 5, choose 4, and this is combination of 5, choose 5. And that's very convenient. It's very convenient because look at this. The fifth row depends on this. So if I have a plus b to the 17th, okay, so all the combinations, all the coefficients can be derived by you doing combinations. We don't have to draw out the whole Pascal's triangle. So let me write out some of these combinations for a plus b to the 17th. The first coefficient is going to be combination of whatever the exponent is, 17, and all of them are going to be combination of 17s like this. You're always going to be picking from the 17th row, so to speak. 17th like this. So all going to be 17th. And then the first coefficient is going to be 17 picking 0, and then picking 1, and picking 2, and picking 3, and picking 4, all the way up to combinate. The last term would be 17th picking 17, and there's only one way of 17 picking 17. There's one way, same thing over here. So now that's kind of powerful if you understand what we just did. In other words, we can use this knowledge to generate any binomial expansion. Okay, to generate any binomial expansion, then, for example, we'll give you another example. We have a plus b to the 8th. All right, so there are two things that we have to do. First, we have to write the a's and b's, so it's going to be a to the 8th, the first term, and b to the 0. I'll just write that over here. And then it's going to be a to the 7th, go down by 1, and b to the 1st, and they'll add up to 8. And then it's going to be a to the 6th, and then b squared, and kadhalik is going to go like all the way like that, dot, 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 all the way to the end, a to the 0. Let me write that down, a to the 0, and b to the 8 like this. And then you can get the coefficients either by drawing out the Pascal's triangle, or you can use the combination. So this is going to be a combination of, you're always going to choose from 8. Okay, combination choose 8, combination choose 8, combination choose 8. And then you always start just like the Pascal's triangle, you start out with 0. 8 choose 0, 8 choose 1. Let me write that in a different color. 8 choose 0, 8 choose 1, 8 choose 2, all the way over here, 8 to 8 choose 8 over here. Okay, so this, if you wanted to, is the same as b, but either way you do it, you can get binomial expansion this way. So to expand binomials, all right, so we have to do two things. First, you have to write the a's and b's, so to speak, and then you have to get the coefficient of each term. And the coefficient of each term you can derive using Pascal's triangle or using combinations like we have suggested over here. Now, there's another way of writing this beautiful, elegant binomial theorem, and we shall talk about that, inshallah, next time in the sometime in the future. But until then, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alamin. Assalamu alaikum.